Okay, hi everybody, welcome to lecture 9. In this lecture we're going to talk about a confirmatory factor analysis. So what exactly is that? Well, last time you'll recall that we used exploratory factor analysis to explore potential factor structures from data. So what does that mean? Well, that means that we looked at a collection of items and some observations on those test items, and we essentially reduced all of that variability into factors or dimensions. And we used exploratory factor analysis to talk about how many factors or dimensions are required to describe that data and which items load onto these different factors. So which items cause the variation in these dimensions or these factors. So that's all last time. This time we're going to use confirmatory factor analysis. And what we're going to use that for is to take those factor structures that we looked at last time, and we're going to test these factor structures and furthermore estimate their components. Now, what exactly does that mean? Well, to do this, we need to talk a little bit about measurement in this context. So we're going to talk today about measurement models and path diagrams. And then at the end, we will talk about how to do confirmatory factor analysis in JASP. So let's first talk about measurement models and path diagrams. And I want to motivate this example by beginning with a very basic question. And that is, how do we measure temperature? Well, of course, the silly answer is we simply look at a thermometer. But when we do that, when we measure temperature by looking at a thermometer, we are making some assumptions. We are assuming first that temperature causes the reading on the thermometer, and we're also assuming that the thermometer has relatively little measurement error. So of course these are assumptions that we take for granted, but we could build what's called a measurement model to express these relationships. And you see a picture of it down here. This is kind of a typical notation for what we are going to consider as path diagrams or as measurement models. Let's look and see what all of this stuff means. Well, what we have here is we have the sun, and the sun is causing causing variations in this thermometer. So we call the sun a latent variable. It's not observable. And of course, the reason it's not observable is if you looked at it and actually observed it, you would burn your retinas. So the sun is our latent variable. The thermometer is our observed variable. We can see variations, we can see variance in these thermometer measurements. It has another name that we're going to use quite a bit today, and that is that it is also called an indicator of the latent variable of the sun. So we have these what are called nodes. These are both nodes. Okay, whoops, that was very bad writing, so let me rewrite that. There we go. And we'll talk more about nodes as we go on. We also have arrows in this model. Now these arrows that are unidirectional, these are causal effects. So you notice we have two of them that have one direction on them. We have a causal effect from the sun to the thermometer. So that just tells us that the sun causes changes in the thermometer. We also have one over here. This thing over here is an error node. This is your measurement error. And so what this diagram is telling us is that what we're seeing in terms of variation in this measurement instrument, in this thermometer, is we're seeing variation that's due to two sources. Variation from this latent variable of the sun and variation that comes from the error of the instrument itself. Now, of course, this will remind you a lot of classical test theory. This is just another way to look at that same relationship. There are also some other arrows in this diagram, and they are sometimes called bidirectional links, so we could write them with two little arrows on the end, and these simply indicate variances or covariances. So for example, this right here, this little bidirectional arrow is going to tell you that there is variance in the measurement error, and this one over here will tell you that there is variance in the latent variable. So essentially we have a lot of information about this relationship of measuring temperature that is encoded in this model. And so what we're going to do is we're going to use this as a metaphor for building more general or more abstract measurement models, and then testing whether those models are reasonable, and furthermore estimating what the components of those models are. So let's move to a bit more of an abstract example. Now here's a very abstract example that seems to have no meaning right now, but this is sort of your first example of what we call a path diagram. So it looks in structure almost identical to the sun example that we just looked at, but now these could represent more abstract psychological constructs, and we'll look at examples of those at the end today. But let's talk a little bit first about the notation that is used in one of these path diagrams. So in these path diagrams, the circles that you see, these are your latent or unobserved factors. So kind of like the sun that we had in our previous example. The squares, they represent the observed variables. So these are typically the things that you measure. And then of course we have a circle on this epsilon 1. That's an error node, and that's of course something that's latent as well. And then in this diagram we say that eta 1, now by the way, let me write these down. There are a lot of Greek letters that are going on here that you might not be familiar with right now. This one looks like an N. It's actually a Greek letter eta. And of course this is a Y, so there's nothing weird going on there. This one looks like an E. It is an epsilon. Okay. This one over here you're probably familiar with. This is a theta. This one over here is a psi, or sometimes people really emphasize the P on it and call it psi. I don't like doing that, but there you are. And then finally, this one up here, this is called lambda. Okay, so just so we know what these Greek letters are called. Okay, so this relationship that you're seeing here is that y1 is indicated by eta 1. This is a factor that causes variation in some observed variable. Now this diagram is encoding more than just that causal relationship. It's also encoding some error, and it's particularly encoding an effect of this factor on y1. And the equation for that effect is given right down here. This says that y1 is equal to lambda 1 times eta 1 plus epsilon 1. What exactly does that mean? Well, let's scroll down just a little bit. What that means is that lambda 1 is the loading of factor eta 1. I want to try to get both of these in the same window. There we go. That lambda 1 is the loading of factor eta 1 onto observation y1, and epsilon 1 is the measurement error. So this is telling you that the true value of y1 can be gotten by taking lambda, the loading, times the factor plus some error. So it's just a linear relationship between the factor and the observed variable. So factor analysis is just a linear model. There's also some other things that are going on here. You'll see that there are variances here. We have theta 1 and we have a psi 1. What are they? Well, theta 1 is the variance of the error term, and psi 1 is the variance of the factor. Now, what exactly do we mean by that? Well, we say two other things. Now, this is some mathematical notation that I'll explain in each bullet. The first one is that we assume that eta 1 is normally distributed with a mean of 0 and a variance of psi 1. Okay? So eta 1 is assumed to be normally distributed around 0 with a variance of this term psi 1. This is sometimes called the factor variance. And then epsilon 1 is assumed, the error term is assumed to be normally distributed around 0 with a variance of theta 1. So theta 1 is sometimes called the residual variance. It's the extent to which you vary around an error term of 0. Okay. So that's a lot of technical information about the model, but the good news is this basically just gives us some things to do in confirmatory factor analysis. Particularly, our goal is this. We're going to take some observed data and we're going to estimate these unknown parameters of the model. What are the parameters? Well, from the picture that we saw, let's scroll back up there, all of the things that we have to estimate from the thing that we're given here. We're just given one of these, right? It's just the observed data. The rest of it we estimate. Those estimations are the factor loadings, the factor variances, and the residual variances. So our goal now is going to be to estimate these and see how well it fits the actual observed data. So to fit these data, we're going to use what are called structural equation models, okay? And we must make sure, this is kind of a technical condition, but we have to make sure that two conditions hold. The first condition is that we have to scale the factors. So you think about it this way. If you are measuring temperature, you're going to measure using a thermometer. That thermometer is either going to be on the Fahrenheit scale or on the Celsius scale. They're both valid, but you have to pick one, and then all of your measurements need to be based on the same scale. Otherwise, you can't compare one measurement to the other. So in general measurement models, these so-called structural equation models, we do this by one of two ways. We either set one of the loadings from each factor equal to 1, or the one that JASP does, and I actually like this one, we set the factor variances equal to 1. Okay, so what does that mean? Well, what that means is in this general model up here, instead of having an additional parameter for the factor variance, we would say just get rid of that, set that variance equal to 1, and then down here in this assumption, we now assume that the factor is normally distributed around 0 with a standard deviation of 1. Okay, so it essentially reduces a little bit of the variation in the model. So it's one less thing to fit. So this is the one that we're going to do. We're going to always assume that we set the factor variances equal to 1. And again, notice that JASP will do this by default. It'll sort of happen underneath the scenes and you won't even know it's happening, but I will make a mention of it in the example later. So that's one thing. The other technical condition that we have to do is we have to make sure that the number of observations, that is the observed variances and covariances from the data, must exceed the number of parameters, so the factor loadings and variances and residual variances. The amount by which the number of observations exceeds the number of parameters is called the degrees of freedom. Now, you've used that term a lot before in hypothesis testing, but we've probably never told you what it meant. Well, this is exactly what it means. This is the extent to which the number of observations exceeds the number of parameters. If these two conditions hold, so these two conditions are, you scale the factors by setting the factor variances equal to 1, and your number of observations exceeds your total number of parameters, we say that the model is identified. In order to fit a model, you have to have an identified model. So let's do some examples and let's see if our models are identified. So what we're going to see here are several examples of path diagrams. And I'm going to show you in each one of these how you actually go through and check to see if the models are identified. So here's that first example that we did. Now remember, first thing that we do is we set the factor variance equal to 1. So I'm going to set that equal to 1. So now that's no longer a parameter. Let's first say what are the number of observations. Well, the number of observations are the number of terms that you have plus any covariances between them. Well, we only have one term, this is this y1, and there's no covariances between them, so we simply have one observation. It's simply that square node that we see right there. What about parameters? Well, if we look at parameters, we have a parameter for the loading, and we have a parameter for this theta, this error variance or residual variance. You may ask, well, what about eta 1 and epsilon 1? Well, these are latent variables who are assumed to be normally distributed with these variances. So really, the only parameter in the model is the variance itself. Now, if you forgot and didn't actually identify the model by setting, or sorry, scale the model by setting this equal to 1, you would actually say I had 1, 2, 3 parameters. But that's technically incorrect because we first have to scale the model by setting that variance equal to 1. So we really only have 2 parameters. We have lambda, the loading, and we have theta, the residual variance. So what are the degrees of freedom? Well, the degrees of freedom are the number of observations minus the number of parameters, which is 1 minus 2, which is a negative 1. Now, if that sounds a little bit strange to you, that's because you can't have a negative degrees of freedom. This means that the model is not identified. What that means for us is we can't fit this model. So if we were to simply try to take some data and fit it to this model, it wouldn't work. This absolutely is not enough. And so such models will never be seen in a structural equation modeling or confirmatory factor analysis context. You simply can't do it. Okay? So let's try a different example. This one looks a little more complicated, but maybe there's just a chance that it is identified. Well, again, first step in identification is to set the factor variances equal to 1. I almost said 0. Set them equal to 1. And now we look, what are the observations? So you may look at this first and say, well, there's 2 observations, right? But there's actually more than that, because what the observations are the variances and the covariances, the observed variances and observed covariances. Okay, so we have an item here and an item here, so each of these has a variance, and there's also a covariance between them, right? They're related to each other, and so our number of observations is 3. Now, if you're worried about counting here, I'm going to show you a shortcut on the next example, but just keep in mind, sometimes this is not too intuitive, so that's why I'm going through it pretty slowly. The number of observations is 3. Now, what about number of parameters? Well, our parameters are the loadings, so we have 2 loadings, and we have factor variances, but those aren't parameters here because we set them equal to 1. And then we have residual variances. These are the thetas, right? Theta 1, 1, and theta 2, 2. So there's 2 of those. So this is a total of 4 parameters. Okay, so you can already start to see the same thing is going to happen here. The degrees of freedom is the number of observations minus the number of parameters, which is 3 minus 4, which again is negative 1. This model is not identified. Oh my goodness, what is going on here? Well, what this says is you can't estimate a model that only has 2 items loading onto 1 factor. It's just not going to work. Okay, so let's see how many do we need to have? Well, 3 do it. Well, let's try that out. Let's do a model that has 3 items loading onto 1 factor. So let's do the same exercise here. Again, we'll take the factor variance, scale it to 1. Now, number of observations. So let's take this carefully. We have 3 observed variables, y1, y2, and y3. So there are 3 variances that we would observe. But we also have to count the covariances, right? So there's a covariance between 1 and 2. There's a covariance between 2 and 3. And there's a covariance between 1 and 3. So we actually have the 3 observations, the 3 variances, plus the 2 covariances in between, plus the 1 on the outside, which actually gives us 6 total observations. Oh my goodness, so what is going on here? Well, there's actually a really nice formula that you can use to figure this out. This is the shortcut, and you're going to really need it on the next example. So if you have P observed variables, then the number of observations turns out to be P times P plus 1 over 2. There's a really elegant reason for why that's the case, but I don't want to get into that in this lecture. But if you are interested in the mathematics of why this works, it is beautiful, and I would invite you to visit with me about that sometime. Let's try that little formula here. We're supposed to get 6 total observations. Do we get it from this formula? Well, we have 3 observed variables, right? So this is 3 times 4, 3 times p plus 1, over 2, that's 12 over 2, which is 6. Okay, so that is 6 observations. Again, remember, what are you doing? You're counting the variances as well as the covariances between each of the items. What about parameters? Well, we have our 3 loadings, and we have our 3 residual variances. So we have 6 parameters. Oh, look at this. The degrees of freedom, the number of observations minus the number of parameters. Well, there were 6 observations. There are 6 parameters. This degrees of freedom is 0. This is identified. Okay? It is identified, but it is only just identified. And we actually call this a saturated model. Another way to look at this is it is an exact fit. So in terms of fitting the best model, there is one unique solution to this model. To figure out what I'm talking about here, think back to college algebra when you were doing things like 2 equations with 2 unknowns, right? So essentially you had 2 observations, you had 2 variables, you had no degrees of freedom, right? There was only one solution to this. That was your first example of a saturated model, even though we didn't call it that back then. Okay, so here's a model. It's identified, but it is a saturated model. All right, now here's one that's a little more complicated. In fact, I'm going to zoom out just a little bit on this one. I'll come back in a moment. So here we have quite a lot going on. We have 2 factors now, eta 1 and eta 2, each with 3 observed variables that are being loaded onto those factors. Notice the notation: lambda 1, 1, lambda 2, 1, lambda 3, 1, and then lambda 4, 2, 5, 2, 6, 2. So when you have lambda sub I j, so the I is the item and j is the factor. Okay. Again, just a little bit for the notation there. You'll also see this in JASP, so I want to make sure you knew what this notation meant. So what's going on here? Well, again, remember, we identify the model first by setting the factor variances equal to 1. Okay, so there's 2 of them to set equal to 1. Now you may wonder, what is this thing right here, this psi 2, 1? Well, this is a covariance between factors, and that's actually a parameter in the model. We don't have to set that one equal to 1. Now we have 1, 2, 3, 4, 5, 6 variables, so the number of observations is going to equal 6 times 6 plus 1 over 2. Okay? Because what we're doing is counting not only those 6 variables, but also all of the combinations between them. And if we do the arithmetic here, this is 6 times 7 over 2, which is 42 over 2, which is 21. So there are 21 observations, 21 observed variances and covariances in this model. What about number of parameters? Well, again, the number of parameters is going to be your loadings. So there's 6 loadings. There are 6 residual variances, these thetas down here. And then there's 1 covariance, right? 1 factor covariance. And so this adds up to a total of 6 plus 6 plus 1, which is 13 parameters. So what are our degrees of freedom? Well, degrees of freedom is always the number of observations minus the number of parameters, which is 21 observations minus 13 parameters, which is 8 degrees of freedom. So this is most certainly identified. Okay. So again, what does that mean? That means that this is a model that if we put it into some software like JASP, we could actually get a model fit, right? We could actually get something out of this. I want to do a couple of more examples of what these models could look like. We won't talk about how to fit these specific ones today, but just to give you an indication that this can be as general as you want, let's go to the next page. You may notice that this model looks very similar to the last one, but there's one extra thing. It's right here. Let me zoom back up to, oops, that's a little too far. I'm going to go about to 120%. So we'll take a look at this one right here. You'll notice there's one extra. Let's get rid of those, set those equal to 1. We've got this extra loading right here. This is called a cross-loading. This is not something that we've looked at before, because last time when we were trying to achieve what we called simple structure, we wanted to make sure that each factor uniquely was loaded by items. Here you have actually one item that's loading on two different factors, and that's why we call it a cross-loading. What does that do to our estimation? Well, again, the number of observations is the same here because we've got these 6 observed nodes, so that's the 21 variances and covariances. So that's just the same as last time. But what about parameters? Well, parameters, we've got a covariance here, a factor covariance. We've got 1, 2, 3, 4, 5, 6, 7 factor loadings and 6 residual variances. So we've got 1 plus 7 plus 6, which is 14 parameters this time. And so when we go to compute our degrees of freedom, it's the number of observations minus the number of parameters, which is 21 minus 14. That gives us degrees of freedom of 7. So this is still an identified model. Okay, so we can fit it, but it has fewer degrees of freedom than the other model. In other words, it basically says that you have more parameters to fit given the same data. So there's less freedom for those parameters to vary. Okay. Then finally, let's look at some other ways that you can complexify these models. Again, let's set the factor variances equal to 1 to identify or to scale. Here we have almost exactly the same as the first, but now we have a residual covariance. So this link between 2 residual error terms, this is called a residual covariance. So number of observations is the same, it's still 21. The number of parameters, it's almost the same, right? We've got 1 factor covariance. That was the Psi21 that we saw up here at the top. We've got 6 loadings. But this time we've got 1, 2, 3, 4, 5, 6 factor variances, or sorry, 6 residual variances and 1 residual covariance. So we've got 7 residual covariances and variances, which I'll just indicate that way. So that gives me a total of 14 parameters. And so our degrees of freedom, just like in the very immediately past example, it's the number of observations minus the number of parameters, 21 minus 14. Turns out to be exactly 7, just like before. So again, we have an identified model. Quick note, we're not going to do anything as complex as these past 2 models, so having residual covariance or having cross-loading, that'll be for the next lecture, but just know that it can happen and you can still fit these models. Okay, so that's a little bit about the theory part of structural equation modeling, and particularly confirmatory factor analysis. That gives us that gets us accustomed to the language that we use, but I want to talk now about actually fitting this model in JASP. So what I'm going to do is introduce the example that we did last time, and I'm actually going to switch over to my other laptop to finish out the recording so that I can use JASP. So if the video looks a little different here in a few minutes, that's the reason why. So let's try doing this. Now remember last time we were measuring statistics anxiety with this so-called SAC-8. So it was an 8-item statistics anxiety questionnaire. Each of the items was Likert scaled, where 1 was strongly disagree and 5 was agree, or strongly agree, and then we had these 8 items. And last time we did the exploratory factor analysis on it, and we found that we basically had two factors. We had a factor for statistics anxiety, which was loaded by items 1, 3, 4, 5, and 8. And then we had factor 2, which was kind of about computers. We called that computer self-concept, and that was loaded by items 6 and 7. So what I want to do is draw this factor structure. So let's draw this model. So what I'm going to do is first draw two nodes for my factors. So my factors were statistics anxiety, so I'll just call that SA, and I had computer self-concept. Okay, so I'll draw two nodes for those two factors. Now between what observations do we have coming from those nodes? Well, we had 5 items. So item 1, item 2, or sorry, item 2 we left out, right? Item 3, item 4, item 5, and item 8. These were all loaded by this statistics anxiety factor. So let's draw causal arrows, and then let's also do some, I'm going to zoom in just a little bit more. Where is my, there it is. So we'll go in here and make my pencil. I'm going to zoom back out. Sorry about that, guys. So let's label these loadings. This would be factor 1, so I'll call this lambda 1, 1. This will be lambda 3, 1. This will be lambda 4, 1. Remember, item goes first, factor goes second. Lambda 5, 1, and then lambda 8, 1. Now, CSC, computer self-concept, that was items 6 and 7. So again, we're putting them in square nodes because those are observed. And then we can also write the loadings. This is lambda 6, 2, and then lambda 7, 2. So those are the factor loadings. We're certainly going to want to estimate those, but we also want to do some other things as well. All right, we will assume that there is some factor variance. And of course, to identify the model, the first thing we do is scale it. So we set that factor variance equal to 1. But then there's also some factor covariance. Okay, so we'll call this psi 2, 1. So this is simply the covariance between factors 1 and 2. And then each one of these will have some measurement error. So error 1, error 3, error 4, error 5, and error 8. And we'll also have error terms for items 6 and 7. And each of these will have their own associated variances. So this will be called theta 1, 1. This one would be called theta 3, 3. Theta 4, 4. You may ask why the double index. Well, it's simply because you're saying that this is covariance between something and itself, 5 and 5, which of course we know is just another name for variance. And then finally, let's put these variances on there. This would be theta 6, 6, and then theta 7, 7. Okay. So there we are. First thing that I want to do now, I don't think I'll actually mention this when we go to the JASP screen because it turns out I've already recorded that part. I can't go back in time and re-record it, but check when we go over to JASP and see if we got this right. So let's compute the degrees of freedom for this model. Let's see that it's actually identified. Well, so what do? Number of observations. So we have 1, 2, 3, 4, 5, 6, 7. 7 observed nodes, so the number of observations would be 7 times 8 over 2. So that's 56 divided by 2, which is 28 observations. What about the number of parameters? Well, let's go up and count. We've got 1 factor covariance, we've got 7 loadings, and we've got 7 residual variances. So 1 plus 7 plus 7. So that's what, 15? And so the degrees of freedom is going to be the number of observations minus the number of parameters, which is 28 minus 15, which is 13. So when we go to the JASP part here in just a couple of seconds, check when we do this and see if we actually do get 13 degrees of freedom. So I will see you when we open up JASP on the other computer. All right, so you can see that I have opened up the PSYC8.csv dataset in JASP, and this is what it looks like. Here are the 8 items. Now you might remember from when we did the exploratory factor analysis that these items are automatically encoded as ordinal level variables. Now, of course, remember, one of the assumptions in a factor model of the kind that we're discussing in this lecture is that these items are normally distributed. That assumes, of course, implicitly that they are scale variables. They are on an interval or ratio scale at least. So we're going to indicate that first for each one of these items. We just need to go through, click on the little icon that indicates the level of measurement, and change each one of them to scale. So we'll do that first. This is a little tedious if you have a lot of variables, but we don't here. So now we want to build our model. So we'll go up to the Factor tab, or the Factor button, and we will select Confirmatory Factor Analysis. We already know what our proposed factor structure is, so we don't need to do the exploration this time. Let's click on Confirmatory Factor Analysis. Now this window will ask us to build the factor structure, and we can even give it names if we want. So from what we did last time with our exploratory analysis, we found what looked like 2 factors. One that we'll call statistics anxiety. So I'm just simply going to rename factor 1 as statistics anxiety. And a second factor which we called computer self-concept. These names are completely arbitrary, of course, but I think these are good descriptive names. And then what we want to do is simply drag, highlight and drag the items that correspond or load onto each one of these factors. So for statistics anxiety, that was item 1, and then 3, 4, 5, and 8. What I'm doing on the Mac here is holding down the Command key. If you can't figure out how to just select those without selecting all of them, just do it one at a time. But for me, this works really nicely. And so I can just highlight every one of them that I want to go in the statistics anxiety factor and drag them over. Again, you could also just use that little arrow button to do this. For our second factor, computer self-concept, that's items 6 and 7, so I'll highlight those and drag them over. And you can see that there's already some things happening over in the results side. Now, the thing we need to talk about now is what do we do with all of this? Well, there's sort of 2 things that we're going to do. One is we want to look and see, based on the picture that we drew of this proposed model, what are the estimates? Remember, we had several things to estimate. We had the parameter, we had the loadings of the factors. We assumed the factor variances were 1 each, but we did have a factor covariance, so that will need to be estimated. And we also had residual variances on each of the items that needed to be estimated. Well, you can see in the output we actually have all of those. So under factor estimates, we have a chart of factor loadings. So these are the estimates for the different loadings, and you can see the symbols match what we used in our picture. And we also have an estimate for the factor covariance. That's this one right here. Notice that the estimate for the factor variances is 1 because by default, JASP identifies the model by setting those variances equal to 1. And then finally, we have residual variances. So on each of the items that we put in the model, we have an estimate for these thetas here. So that gives us the estimates. You can actually, is really a cool thing in JASP, you can make a plot that's a nice formal version of the model that we drew just before doing this JASP thing. If you go to plots and select model plot and show parameters, you will see a plot that should look very similar to the one that we drew. And in fact, you can see each one of the parameters that this model estimated. You can see our identified matrix, our identified variances up here. You can see the estimated covariance. You can see each of the loadings, and you can see each of the item residual variances. Now, I do want to point out something. In the method for confirmatory factor analysis that we've been talking about, remember we identify the model by setting the factor variances equal to 1. That's what gives us a scale on all of the model estimates. There's another way to do this. The other way, and I mentioned this earlier in the lecture, is to set usually the first loading equal to 1. How do you do that in JASP? Well, what you can do is go to Model Options, and here where it says Factor Scaling, instead of choosing factor variances, you can choose Marker Variable. And you'll notice what that does to the picture is it sets the first loading equal to 1, but then what happens after that is you get estimates for the factor variances now, instead of just setting those equal to 1. Now, of course, by doing this, the numbers all change, but it's all fitting the same data. It's just scaling it in a different way. It's the same thing as if we measured the temperature in Fahrenheit and then measured things in Celsius. The numbers are different, but the model, the temperature model with the thermometer, is the same model. This is not how I want to do it, though. I'm going to go back to using factor variances, and you don't even have to mess around with this, but I just want to show you that that's how it's done. So those are the estimates. So I can actually go in and fill out my model that I drew earlier with these numbers, and this little plot in JASP gives us a nice way to see that. Now, what else do we do with this? Well, we've got the estimates, but we would also like to know, how does the model fit? So let's talk a little bit here at the end about how the model fits. Here's basically the quick and dirty of what happens. What happens is that JASP computes a fit statistic, and we're going to call it capital T. It is beyond the scope of this lecture to talk about what T actually is, but it's essentially a maximum likelihood estimation. It's a likelihood given the observed data. But what do we do with it to assess fit? Well, what we do is we assume a hypothesis, a null hypothesis, that the model fits exactly. That is, that it is the saturated model that we described earlier. If that hypothesis holds and the model fits the data exactly, then we know just through statistics that this T statistic is distributed as a chi-square distribution. Now that's fortunate because we know a lot of things about chi-square distributions. We know the probabilities of getting certain data under that distribution. So what JASP does is it reports a chi-square test. And here's the way it works. It's a little different than most hypothesis tests that you might be used to. If p is less than 0.05, so if your data are pretty rare under this null, then that actually implies that the model does not fit, because you're rejecting the hypothesis that the model fits exactly. So really, in this case, p less than 0.05 is a bad thing, because this says that you're way different than your supposition of a model that fits exactly. On the other hand, if p is bigger than 0.05, then we accept the null, which then implies that the model does fit. So I want to highlight both of these and point this out. This is completely opposite of what most hypothesis testing situations are that you would be accustomed to. In these kinds of model fit type tests, you actually don't want to reject the null, because the null is the hypothesis that you want the evidence for. The null is the one that says that this model fits your data. So we want p bigger than 0.05. So yeah, let's go take a look real quick and see what JASP gives us with regard to that. It's actually up at the top of that output. It gives us a chi-square test, and it gives us two things, but this factor model here is your statistic. This is the t-score that I was telling you about. It's 66. Here's the degrees of freedom for the model, which you could compute the same way we did earlier, but notice that the p-value is less than 0.001. So if you didn't know anything about confirmatory factor analysis and you weren't watching anything in the lecture up until now, you would think, hey, this is good, my model fits. That is actually completely false. Because p is less than 0.001, go back here, this means we're actually rejecting the null which is a hypothesis of exact fit. This actually implies that the model does not fit our data. That's unfortunate, right? That's very unfortunate. So what is going on here? Did we just have a bad model? I mean, we were pretty confident based on our exploratory factor analysis that this was a good model structure for the items in the SAC-8. Well, here's kind of the thing, all right? The chi-square test is just like any other hypothesis test. The bigger the sample size, the more power it has. And so what that tells you is that for large N, if you have a lot of data, this chi-square test will actually tend to reject models even when the fit is close. All right? So it could be the case that we have a very close fit, but we're rejecting the model because we have a large N. Is that the case here? Well, if you remember our original data set, we have a lot. I'm going to scroll all the way down to the bottom. We have an N of 2,571 observations. That's a very large N, and that could potentially be the reason that we're rejecting the null, even though it's actually a reasonably good fit. So for this reason, and this is a really big thing, for this reason the chi-squared test isn't probably the best model fit statistic to use. There are better ones, and I want to introduce you to one today as we finish up. And that alternative method is called RMSEA. We actually introduced this in the last lecture just briefly. What it stands for, if you'll remember, is root mean squared error of approximation. It's different from chi-squared in that it is a measure of absolute fit. There's no comparison model. You're not supposing that you're starting with a saturated model and then measuring the difference between your data fit and that model fit. It's just a measure of absolute fit for the model itself. So there's no comparison. In general, the smaller your value, the better. And there are some guidelines that are published. If you have less than 0.05 for this RMSEA, that's typically considered a very good fit. If you have between 0.05 and 0.08, that's typically considered as a good fit. Not a very good one, but a good enough. And then if you have bigger than 0.08, that is typically considered as an unacceptable fit. So let's take a look at JASP here in just a second. I do want to mention that RMSEA is kind of a cool index because it's one of the only fit indices for which the sampling distribution is known. And if you know that, that means you can compute confidence intervals. And so not only can we get an estimate of this root mean squared error of approximation, but we can also get a 95% confidence interval. And that's given to you in JASP. How do we do that? Well, let's go back to JASP and see. Now, we didn't choose any options on our confirmatory factor analysis. All it gave us was, for model fit, the chi-square test. Well, if you go to additional output and select additional fit measures, it will give us a whole bunch more. And in fact, one of them that you'll see down here in the third box is root mean squared error approximation, RMSEA. And you can see that we get a value of 0.04. That is less than that threshold of 0.05 that we mentioned, so we would consider this a very good fit. In fact, it gives us a 90% confidence interval between 0.031 and 0.05. So we can be 90% confident that we have a very good model fit. And so that's a much better index because that, I think, is better reflecting the fact that this is a good model and that fit is not getting taken away or penalized by the fact that you have a very large sample size. So chi-squared and RMSEA are the two main model fit indices that we'll consider today. In the next lecture, where we talk about a little bit more general structural equation modeling, we'll talk about some others of these indices, and we'll also talk about the information criteria, particularly AIC and BIC. But that's next time, and that really only comes in when you're trying to now compare different models to each other. But as a model of absolute fit, RMSEA is the one to go. Okay, so that's it. That's confirmatory factor analysis. Again, just the basic rundown. With exploratory factor analysis, you get a potential factor structure. You can actually test and estimate that factor structure when doing confirmatory factor analysis. And it is a subset of something more general called structural equation modeling, which is a very powerful technique. So that's all for now. Next time we will look more at structural equation modeling, and in JASP we'll learn how to use the SEM module to do some of this model comparison. So that's all for now, and I'll see you next time.